Okay, good morning, everyone. Today is the last remaining circuit analysis technique, superposition. I believe we talked about it a little bit in last class. So we'll complete the theory and cover the example in this class today. And after that, it'll be only the application of the analysis techniques to larger theorems. Yes. It should have been Saturday. It's not updated on Canvas. Let me take a look. It should automatically be updated. So at my end, when I looked at it, so can you repeat that? Ah, okay. Gotcha. It's weird. Was not aware of that. Thanks for letting me know. So at my end, when I look at it, it shows February 3rd, which is tomorrow. So at your end, the date and the grades are both from Wednesday, if I understand you correctly. That's weird. It should be the same for both, right? At my end, it shows February 3rd on Canvas. Let's see if I do student view. Let's see. No, even in student view, and I checked, it still showed me February 3rd, just tomorrow. I don't know. Okay, all right, let's see. Section 3, superposition theorem. Okay, so superposition theorem applies to circuits, larger circuits, which have multiple sources. And when we have multiple sources that we cannot reduce, we apply mesh current analysis or node voltage analysis, right? Superposition principle allows us to actually apply the simpler technique of series parallel equivalent analysis, which is where we reduce a large network of resistors down to one single resistor and then solve it that way, right? So applying simpler analysis techniques. The way we do that is by breaking up the circuit into multiple parts, and then you analyze each part separately. When I say breaking it up into multiple parts, it relates to the number of sources that are present in the circuit. Okay. If a circuit has more than one source, whether it's a voltage source or a current source or a mix of both, could be 2, 3, 4, 500 sources in a circuit. You could break it down into n number of parts, n being the number of sources present in the circuit, and then analyze with only one source working at a single time. And the rest of the sources are turned off or reduced to 0. Okay. So superposition basically states if you have n number of sources in a circuit, the voltage or current at any single point in a circuit is a result of all of those n sources working at the same time. So if I was to find a value for RT, where R could be voltage or current, and T is the number of T would represent the quantity or the number of parts for that quantity depending on the n number of sources. So it would be 1 plus 2 plus 3 all the way to n. Okay, so RT would be R1 plus R2 plus R3, so on and so forth until Rn. Basically, n number of parts, you add it all together, that total would be RT. And again, R could be voltage or current. Obviously, the advantage is that each piece or each part of that circuit can be analyzed in simpler terms by applying simpler analysis techniques. But the downside is the more number of sources you have, the more analyses you have to perform. If you have 2, then you have to perform twice as many analyses. If you have 3, so on and so forth. So if you have like 3 or more, it just becomes very time consuming and laborious. So it's highly inefficient. Okay, so that's the downside. And some circuits are not reducible, even if they have only one source. And so at that point, you would apply superposition first, you break it up into individual parts, and it may turn out that you would have to apply node voltage or mesh current analysis for each one of those parts. That kind of defeats the purpose. If you want to apply mesh current or node voltage, you would apply it at the beginning itself. We don't want it to apply it after we apply superposition. Does that make sense? Right? The point is to keep things simple. So when we say analyze with only one source at a time, we mean that only one source is active at a time. All the other sources in the circuit are inactive. We reduce them to 0. And when we reduce them to 0, we replace it with either open circuit or a short circuit. And the logic behind that is this. If you have a voltage source in a circuit, doesn't matter where it's connected. Let's say this is A and B. VAB is the value of that voltage source. Let's call it Vs. The only way VAB is equal to 0 would be if they are both at the same potential, right? If either point is higher than the other, then you have a difference in potential, then you have a voltage between the 2 points. But if both of them are the exact same potential, then VAB is equal to 0. The only way both of them are the exact same potential is if you place a short circuit wire between the two. So you remove that voltage source and you replace it with a wire. This way, VAB measured between the 2 terminals is equal to 0. There is no difference in electric potential because there is a wire running across. Does that make sense? Again, this is just a concept, okay? This is conceptual, but more importantly, you have to remember that the voltage source is replaced with a short circuit. Similarly, there is a reason why we replace a current source with an open circuit. It's the exact opposite of this. The only way a current cannot flow through a path is if there is no path to flow through. So if you want to reduce a current source to 0, you simply take that current source out of the circuit and replace it with an open circuit, or basically don't replace it with anything. And so a current source, doesn't matter which direction it is going, IAB is the current source IS. The only way it gets reduced to 0 is if there is no pathway for the current to flow through. It's replaced with an open circuit. So this is a short circuit. This is an open circuit. And so I can say current IAB or IBA is equal to 0. Again, conceptual is just a concept, but the more important point is up here. Reducing an independent source to 0 means replacing a voltage source with a short circuit and a current source with an open circuit. You can have this on your equation sheet. Okay, you can have this on your equation sheet, but of course you should know how to apply, when and how to apply this. Make sense? All right, 10-second pause. Let me know if you have any questions. Any questions at all? Okay, then let's move to an example. Simple circuit. We have two sources, Vs and Is, one voltage source, one current source. It does not really matter what the source is actually. But we are asked to solve for the current I2 using the principle of superposition. I2 is already given to us right here. It's the current that is flowing between R2 and R3. Okay, R2 and R3. Vs is 10 volts. So now that's rainbow colored. 10 volts. R1 is 5 ohms. R2 is 2 ohms. R3 is 4. And Is is 2 amps. We're asked to use superposition. The first step is, of course, to set up the problem correctly. Two sources in a circuit, n is equal to 2. So 2 parts, 2 separate analyses. And you're only trying to find one quantity, I2. Okay, I2. We're not even trying to find any of the other quantities in there, which is like VR1, VR2, or VR3. Okay, you have to perform 2 separate circuits, 2 analyses to find one single quantity. So I'm going to do this. First, I'm going to note this as circuit A, where Vs is active and Is is equal to 0. Right? We are taking it one source at a time, meaning one source is active. All the other sources in the circuit are reduced to 0. In this case, we only have Is. Reduce Is to 0, meaning we replace Is with an open circuit. And so, replace with open circuit. And then you redraw the circuit after you make the change. That way your problem setup would be correct. Okay. It is important to note, it is important to keep in mind that the circuit would change. The change could be very simple, the change could be very drastic. Okay, the circuit is different from the original circuit itself. So be very careful when you're doing that. So we redraw the same circuit. This time, with only Vs. And then Is is, of course, open circuit. You can either choose to just leave it as it is, as I've drawn it right here, which is perfectly fine, or just for explanation purposes, I tend to draw it out. This is the open circuit where Is used to be. Okay. Again, you do not have to draw those terminals. I'm drawing those just for purposes of explanation. And then, of course, we have R1, R2, and R3. And this is Vs. And I2 is coming down here. Since I'm calling this circuit A, I will note this current as I2A. I2A. Okay. Let me note it here. Vs is A, Is is B. This would be I2A. This would give me I2B. Everyone with me so far? Okay. All right. Then what do we see? What is the relationship between R1, R2, and R3? They're all in series because they're all connected by 1 point each. So the entire circuit is in series. It is now a one-step application of Ohm's law, and we'd be able to find I2A. Right? R1 is connected to R2. That junction point is not connected to anything because the current source is now removed. So there are only two components at the junction point. So R1 and R2. Remember, I just said circuit changes, right? So due to that circuit change, R1 and R2 are now in series. R2 and R3 were originally already in series. You can see that right here. One junction not connected to anything. And so now R1, R2, and R3 are all in series, simple application of Ohm's law. And I can write I2A I2A is simply Vs or Req. And Req in this case is simply the sum of all the three resistors in series. So this would become 10 divided by 5 plus 4 plus 2, 11. So I2A is 0.909. Does that make sense? Right. So again, superposition allows us to simplify the circuit by breaking it up into different pieces. Each piece can be analyzed independently, but it's a new circuit, okay? Because of the reduction of the sources to 0, the circuit changes. Because it's a different circuit, your analysis technique can be different. All right, any questions? Well, then let's move into circuit 2, which is only IS being active. And if IS is the one being active, then, all right, first step, let's call that circuit B. I note that IS is active. And when IS is active, Vs is equal to 0. I replace Vs with a short circuit. So Vs is replaced with a short circuit. My circuit changes and becomes like this. Actually, let me go ahead and combine R2 and R3 together. Interesting. I will call this R4. R4 is R2 plus R3, which is 6 ohms. And this remains R1. And this is I2B. I2B. So circuit has changed again. Keep in mind, R4 is not changed. R4 was, you could have done this as a first step also. Okay, the R4 is not due to the change in the source. R4 is simply a series combination of R2 and R3. That's all it is. But take a few seconds, take a look at the circuit, and let me know what you see. Let's label these terminals and mix it. So I'm going to label this terminal as 1. And I will label this as 2. 1 and 2. So 1 is here and 2 is here. What do we see? Absolutely. They are in parallel. Because of the voltage source being replaced with a short circuit, the other end of R1 is now connected to node number 2. And because that happens, R1 is now in parallel. R1 is now in parallel with the current source IS, which is also in parallel with R4. The entire circuit is in parallel. Take a few seconds, pause. I want to make sure everybody understands that. Does everybody see that? Again, this is a simple circuit, and so it's easy to see this. But in real life circuits, when you apply this kind of principle, again, even in problems, when you see this, take a few seconds, look at the circuit, see how it is changing. Because of the open circuit of current sources and the short circuit of voltage sources, connections are either made or they are broken. And so the circuit changes. So again, take a few seconds and look at the circuit first, and then begin your analysis. In this case, we have IS coming down from the top, right? It's coming down, and then it splits or divides. Because it's a parallel circuit, what can we apply? What analysis technique can we apply? Give you more of a hint. It splits, it divides. Current is dividing. Come on. Current division. We can apply current division directly. Or we can find Req, apply Ohm's law, find the voltage across 1 and 2, and then apply Ohm's law to find the current again. Or we can skip a couple of steps and apply current division directly. I'll show you both. So let's see, 1 and 2, right? So we'll find Req. In this case, Req is the parallel combination of R1 and R4. So it is, what is 5 parallel with 6. When you have two resistors in parallel, the Req is the product of the two divided by the sum of the two. 5, 6 are 30, divided by 11. This should give us 2.73 ohms. Keep in mind, this Req is different from circuit A. Circuit A, all three resistors were in series. In here, 2 of them were in series, and they were in parallel with the third one. Okay, so this Req for circuit 2 is different from the Req in circuit 1. It's not the same. Therefore, voltage between terminals 1 and 2 can simply be given by Ohm's law, IS times Req. IS is 2 amps times 2.73. This gives me 2 3s are 6, 27 is 54, 5.46 volts. And then you apply Ohm's law one more time. Because it is parallel, the voltage across 1 and 2 is the voltage across IS, 5.46. It's the same voltage across R4. it is also the same voltage across R1, right? Everything's in parallel. The voltage across a parallel network is a result of all of those components working together. And hence, the voltage remains the same for all components in parallel. And therefore, I can write let me call this current, because we are dealing with, call this current IR4. So IR4 is V12 divided by R4, which gives me 5.46 divided by 6 comes to 0.909. Which is the same as the other one. Yes. Absolutely. That was going to be my next point. I was going to say, what do you see about I2B? Specifically the direction. Because the current source is pointed downwards, the current IR4 is going in the opposite direction as I2B. And if the notation is opposite, then you have to put the opposite sign. So if current IR4 is 0.909, then I2B is minus of IR4 with the same magnitude, which is 0.909. And so I2B is actually minus IR4, and it becomes minus 0.909. Does everybody see that? Take a few seconds, pause, think over it. Let me know if you have any questions. Any questions at all? That makes sense, right? Just because of the changes in the circuit, we applied this technique and we obtained that value. I will show you current division also, but just we'll finish this first and then. So job's not yet done. Total I2 is a summation of both A and B. So I2 is simply I2A plus I2B, which, if we weren't careful about taking the current direction, we would obtain an incorrect answer at the end. There is actually no current flowing through R2 and R3, just because the current source is pointing down. If it was pointing up, the magnitude will still remain the same, but it would be plus 0.9, plus 0.909. Then it will simply be 909 plus 909. instead of it being 0. So always be careful when you're redrawing the circuit. Take your time, because if you set up the problem correctly at the beginning, then chances of error is reduced a lot. Okay, any questions? All right, one final thing to show was the current division. So if I was to solve I2B using current division, I could simply write I2B is minus IR4, so it will be minus IS. Current division principle is fraction of the current source IS flows through that path, and the fraction is given by REQ divided by R4. And so I2B would be minus 2 times REQ. What? That's 2 times REQ is 2.73 divided by R4, which is 6. And you would obtain the exact same answer. Again, it allows you to skip 1 or 2 steps. Now, in a quiz or an exam, if it doesn't state, if I don't ask you specifically to apply current division, you can just do this, which is absolutely fine. If I'm testing you on superposition, then the important point is you should know and show me that you can split up the circuit into multiple parts. After that, you can apply any analysis technique you want. If the circuit is reducible, you reduce it to REQ, one single resistance, and find the voltage and current that way, or any technique you prefer. Apply KCL, KVL, whatever comes to your mind, or actually whatever works for that circuit. Okay. Superposition is up to a point where you divide the circuit into n number of parts. Yes. Well, in just this example, it was current source, but in real life or any other problem for that matter, it could simply be a current that's flowing through that pathway. And you could choose to apply current division as a smaller analysis portion of a larger analysis technique. All right, any questions? So superposition topic introduced and covered. Homework has 2 problems. I won't make it due before Monday, so I'm thinking probably Monday night. So you'd have what, Friday, Saturday, Sunday, and Monday. 4 days, well, nearly 4 days to solve like 2 problems. Quiz on Monday as usual. Topic will be mesh current analysis and perhaps small conceptual assessment of superposition. Okay. I will be available all weekend if you want to talk to me over Zoom. I will also be in my office today until 5 or 6 p.m. If you have any questions, so just reach out to me. But this is the end of the analysis techniques that we have learned. Now we will take all of these analysis techniques and we'll apply it to a larger network theorem. Okay. So from this point on for chapter 2, it's concept. Okay, it's application of the analysis technique, but more it's the concepts. Okay, there's a larger concept, which is a important point. It was an important topic in circuit analysis. Yes. Yes. Well, I might ask short answer questions, or I might just ask, just draw the circuit diagram without doing any analysis, something like that. Yeah. just to assess whether students can, are able to break up a circuit into n parts, that kind of thing. And again, I will post an announcement by 5 o'clock today. Any questions on this? Nothing, right? All right. So then let's talk about equivalent circuits. Very important topic in circuit analysis. You don't have to draw the circuit. You don't have to write it down. You don't have to do anything. Okay. Just listen. Let's say you're working as an engineer for a firm. Your boss or your team is working on a project where you're trying to find the optimal value for R6. Okay, optimal value for R6 because you need the VR6 voltage to fit within a certain spec. Okay, so what analysis technique comes to mind if you wish to find the voltage across R6? We have three sources in there. We just learned about superposition. So we could certainly apply superposition. We could apply mesh current analysis, 1, 2, and 3. Or we could apply node voltage analysis. Node voltage might be a little inefficient with 1, 2, 3, 4, 5, 6, 7. You have lots of nodes in there. So mesh current is probably easier, and as is most cases. But once you find, let's say R6, you experimented with R6 as, let's say, 10 ohms. You did your entire analysis, and you find that VR6 value is not within spec. So you have to change the value of R6. R6 is now, let's say, 15 ohms. What do you have to do? You have to perform your analysis all over again. If not the analysis, at least the calculations, right? You have your equations, you keep changing the values of R6 and keep finding the values again and again and again and again. Well, there was a French telegraph engineer named Charles Thevenin, or Leon Charles Thevenin, or Charles Leon Thevenin. He postulated a theory stating that you could take a circuit and analyze it without that component present and represent that entire circuit as a single voltage source in series with a resistance. And that circuit, that theorem came to be named after him, known as Thevenin's theorem. And the circuit came to be named after him again, of course, Thevenin's equivalent circuit. And this illustration will do it better justice. We have a large circuit. We can represent that entire large circuit with a single voltage source in series with a resistance between the open terminals where a component was connected. And so I could state, actually, let me write this down first. This would be out plus and out minus, simply notations that I'm using. Okay, it does not represent anything. It could be A and B, X and Y, Batman and Robin, doesn't really matter. It's simply noting the terminals where R6 was connected. Okay, so this is where R6 was connected. And again, Thevenin's theorem states that you could analyze the circuit independently of that component and represent that entire rest of the circuit as a single voltage source in series with a resistance. That single voltage source came to be known as Thevenin voltage. VTH is the Thevenin voltage, and RTH is the Thevenin resistance. Important point to note, this is not a new analysis technique. Okay, it is a theorem, it's a concept. you will apply all of the techniques you have learned so far to determine VTH and RTH. You already know how to do this. You already know how to do RTH. You already know how to do Thevenin voltage. Okay. These are the techniques that you have already learned. So you're not learning a new analysis technique. You're simply applying those techniques to determine two quantities. Few years after the Thevenin theorem was published, there was an engineer, telephone engineer working for, I think, AT&T Bell Labs. Not AT&T, sorry, just Bell Labs. And telephone equipment requires the usage of a lot of current sources. You have to maintain constant current. And so he found it easier to work with current sources for his equivalent circuits. And so he postulated his own theory, which was derived from Thevenin's theorem, that you could represent the entire circuit as a single current source in parallel with a resistance. His name was Edward Norton, not the actor, same name. But his theorem came to be named after him, Norton's theorem, or Norton equivalent circuit, and the current source is named as Norton current, IN. So Norton current. Different authors and different books and different papers like to use different notations. Sometimes you might see a notation which is simply VT or capital VT, I mean uppercase, or VTH, everything uppercase. IN could be lowercase or uppercase. They all mean the same thing. I've also seen sometimes RT, so RTH remains the same for Norton circuit. Sometimes if we want to refer and keep things simple, we might also refer it to as RN, Norton resistance, but it means the exact same thing, which is Thevenin resistance. Okay. So three quantities: current, voltage, and resistance. What comes to mind? Current, voltage, and resistance. Actually, just a dot. Thevenin voltage is a product of Thevenin Norton current and the Thevenin resistance. That's the relation between all three. But I will show you why it is advantageous to do this. Is the concept I wouldn't say clear, but does it make sense? And I will show you why it is an advantage. Let's say RTH, VTH, let's say RTH was 10 volts, sorry, 10 ohms, and VTH was 10 volts. If you connect R6 back into the circuit, what is the relationship between RTH and R6? They're all in series. With series, what happens to voltage in a series circuit? What happens to current in a series circuit? It remains the same. So what happens to the voltage? Well, what happens? Voltage division. The voltage across R6 is now a one-step answer. VR6 is simply VTH times R6 or REQ, or you could do VTH or REQ times R6. Plug this into a spreadsheet or a software. You can plug in like 1,000,000 values of R6. It would give out all the values for VR6 in one step. VTH and RTH do not change. I mean, that is the beauty of this application of this theorem. Once you remove R6 from the circuit, the rest of the circuit, of course, remains the same because our job is to find the optimum value of R6. So we analyze the rest of the circuit without R6 and represented by VTH and RTH. That does not change. When we bring it back together, now R6 could take any value it wants, but the answer for VR6 is always in one step, one equation. And then you can just pick and choose which value works the best for your application. That's the advantage. Let's take a 10-second pause, think over that, and let me know if you have any questions. Does that make sense? Yes. Oh. I should say I was trying to test students if they can catch my errors, but that wouldn't be true. That was a genuine error, which happens often. Just notations. So it's VTH or REQ times R6. But does everybody see how the concept is useful, right? And the purpose is, of course, to find a optimum value for that component, which is, of course, a real life problem. Circuit designing is always about trying to find the best value so that our application would work well. The same thing with Norton current. You replace the entire circuit with a Norton current in parallel with the resistance. You can apply current division, and it's a one-step answer to find the current flowing through R6, which would be IR6. Again, one-step answer. Okay. So again, this is not something new. You have already done this. You'd find the Thevenin voltage and the Norton current using, you can use mesh current analysis, node voltage analysis, superposition, any technique you want to find VTH and IN. RTH is simply REQ. We've already done REQ, reducing a large network of resistors down to one single resistance. You have already done that. So again, it's not a new analysis technique. It is simply the application of all the techniques we have learned so far in chapter 2, applied to a larger theorem or a bigger concept. That is all. Okay. It's a guaranteed 30-point problem in the final exam. It runs into 4 pages. It tests everything from chapters 1 and 2. If you've not looked at the final exam page, it has been there since day 1 on the front page of the Canvas site. There are multiple options for you to take the exam, as well as the topics listed on there, which you would need to study. So again, important concept, but it tests everything that we have learned so far. Okay, we'll end class here today. I will see you all on Monday. Quiz on Monday as usual. Mesh current analysis homework is due tomorrow. Superposition, most likely I would set it due Monday night. Topic under assessment is mesh current analysis and the concept of superposition. And I will post an announcement by 5 o'clock today. All right, have a good weekend, and I will see you Monday. I will be available over the weekend, over Zoom, or email. I'm also available today in my office.